Okay, in the previous video we derived conservation of mass equation in differential form. It is also called as continuity equation. In this one we are going to derive momentum equation, which is a mathematical statement of Newton's second law of motion. Okay, so you know that from Newton's second law, rate of change of momentum is equal to the sum of forces acting, and this is stated for a particle in Lagrangian description. So the rate of change of momentum following a fluid particle can be written as the material derivative of momentum, okay, where dv is the volume of the element. Okay, and you know we are talking about a continuum, so sum of forces acting on the particle will be written as the sum of surface and body forces. Okay, so in x direction the rate of change of momentum can be written as x direction d of rho u by dt. Yeah, I'm just leaving the multiplication by volume for simplicity. So the material derivative of rho u can be written as dou of rho u by dou t, okay, plus u by dou y. Okay, just for simplicity we will use two-dimensional version of the equations, and 3D is very straightforward. Okay, in 3D you would write plus w rho of dou u by dou z. Okay, for simplicity we will consider only the 2D versions. Okay, and you know that this is the material derivative, which describe rate of change of a quantity following a fluid particle. This is the local derivative, and this is the convective derivative. Okay, so now this one we know how to write in Lagrangian description. And body forces, to express body force we say let fx, fy and fz denote body forces per unit mass in three directions, in x, y, z directions. Okay, so for example the body force in x direction can be written as fx, which is the force per unit mass, times the mass of the element, so which is rho times dv. Okay, so now we see how to handle body forces, but surface forces here require some careful consideration of infinitesimal elements. Okay, so in order to talk about surface forces, okay, we consider infinitesimal fluid element as we have considered while deriving the continuity equation. Okay, okay, so we consider an infinitesimal fluid element of size dx, dz and dy. Okay, the coordinate axes are x, y and z. Okay, so you know that surface forces are short range forces, which means that only those that are come in contact with that surface will give rise to the surface forces. Okay, so let us consider this right face here. Okay, the effect of the surrounding. Okay, so let's start with the left face. So the effect of the surrounding can be a tensile force. Okay, let's denote that as sigma xx. Okay, and shear in two principal directions, dou x y, and this is sigma x z. Okay, so we are talking about we are actually representing the effect of the surrounding by stress sigma. Okay, so it has two indices I, j. Okay, for example, I can be x, j can be x, y, or z. I mean, I and j can be either one of x, y, z. Okay, so direction I, or the first index of sigma ij, talk about the direction of normal to the considered surface. Okay, we will not talk about whether it is in the positive direction or negative direction. I, the first index represent direction of the normal vector to the considered surface. Okay, so now we started off with this one. The normal is in the x direction. Okay, the normal vector is in the x direction. Okay, so that is why the first index of all three quantities is x, which is the direction of the normal vector to the considered surface. Okay, the second index j denote direction of the stress itself. Okay, so sigma ij represent the stress acting on the surface of the infinitesimal element due to the surrounding. Okay, so we have isolated the infinitesimal element from its surrounding, and sigma ij represent the stresses due to the surrounding. Okay, so the first index I represent direction normal to the considered surface. So we are in this surface, on the left surface, for which the normal is in the x direction. Okay, and j is the direction of stress itself. So this is in the x direction. So the subscript is, second subscript is s. This is in the y, and the third one is in the z direction. Okay. Yeah. I hope this is clear. So now let us talk about the stresses in this direction. So on the left face it is sigma xx. On the right, by applying Taylor series up to only linear terms, we get dou sigma x. So sigma xx plus dou times dx. Okay, so this is xx because the direction of the normal is in the x direction for this surface also, and the direction of the stress also is in the x direction. Okay, now let's talk about y. Okay, so sigma x, the direction of the normal is in x, but the direction of the force itself is, or the stress itself is in y. So sigma y by dou x dx. Okay, so similarly we write this quantity to be, so this one I am writing it here, which is sigma x z plus by dou x dx. Okay, so similarly we can write the stress components on all 6 phases. So we have considered only 2 phases of the element. You can write the same for the other cases. Okay, but in order not to complicate things, I am going to write only the x direction stresses. So if we consider this phase, okay, so let us consider only the stress acting in the x direction. So that would be sigma, the direction of the normal to the surface is y, the direction of the force is x, so sigma yx. Okay, so here it would be, here this one would be sigma yx plus by dou y times dy. Okay, similarly you can write a force acting on the front and back surface for which the direction of normal is in the z direction. Okay, but in order not to complicate this picture, I am not writing that. Okay, so you know that the surface forces arises due to the effect that is in touch with the surface. So physically sigma ij indicate the effect of surrounding. So in this particular case it will be the random molecular motion that is passing through the given surface. Okay, so actually this element is not isolated in the fluid flow, and there will be flux of molecules going through the surface. This effect and the effect of intermolecular attractive forces are described by sigma ij. Okay, that effect we have put together here. Okay, so now let us write the net surface force in x direction. Okay, so if we consider the right face, okay, that would be sigma xx plus dx. This is the amount of stress. Now the force would be multiplied by area, so dy dz. Okay, and on the left face it would be sigma xx dy dz. Okay, now then let us consider the top and bottom surface plus sigma yx this is the stress times area would be dx dz. Okay, so this is again minus sigma yx dx dz. Okay, so similarly there will be two more. So these two terms correspond to the left and right face, and these two terms correspond to the top and bottom face. Similarly there will be another term for front and back face. I am leaving it out to save some writing. Okay, otherwise it will be straightforward to write. Okay, and this concept of stress acting on an element is very, very important. You will see the same in solid mechanics also. Okay, so take some time, understand the concept and the sign convention here. Okay, so now from here some terms will get cancelled. So what do we get is dou sigma xx by dou x. So dx dy dz we have volume plus dou sigma yx by dou y times volume of the element. Okay, so volume of the element is dx dy dz. Okay, so this is in the x direction. Similarly in y direction we get dou sigma xy by dou x plus dou sigma y by dou y times volume of the element. Okay, so before moving further you stop here, you draw all the forces acting on so take a two-dimensional element. If you want, denote all the stress component acting on it, and then try to derive this on your own. Okay, this is very, very important. Okay, good. So let me move forward. So we have rate of change of momentum is equal to sum of forces acting on. Okay, let this we know. Let us denote this equation to be 1. Okay, now we substitute um, this one, and for body forces we have written it here. So we substitute here in terms of this body force, and then for surface forces whatever we have derived we will so when we substitute all these terms, what we are going to get is, so so momentum equation becomes, the left hand side is rate of change of momentum, so that would be rho of rho u by dou t plus v dou u by dou y times dv. Okay, the volume of the element is equal to the surface force dou sigma xx by dou x times dv plus rho fx dv. Okay, I hope this is clear now. This is rate of change of momentum, this is surface forces, and this is the body force. Okay, we have written the equation in x direction. Okay, so multiplying by dv we get dou of dou u by dou t is equal to plus rho times fx. Okay, so this is the momentum equation in x direction. Okay, similarly in y direction we can write plus rho fy. Okay, y direction. So these equations what we have written here, they are called Cauchy equations. Okay, so they are called Cauchy equations. Okay, so until now we have not introduced anything related to fluid here. We just have written the conservation of momentum, or applied Newton's second law to an infinitesimal control volume of a continuum. Okay, so this equation is valid for both solid and fluid media. Okay, so because until now we have not used anything relevant to fluid in this equation. It is just conservation of momentum written in Eulerian description. Okay, that's the only thing we have done until now. But is this equation useful to solve practical problems? No, the answer is no. So Cauchy equation is not useful to solve any practical problems, or for any problem, because if you see the total unknowns here are 3 velocity components plus 6 components of stress. Okay, so we get 6 because sigma is symmetric. Okay, I'm leaving out the reason for why sigma is symmetric. You will learn this in solid mechanics course. Okay, for now you just have to know that sigma is symmetric. Okay, so in total there will be 9 components. Since it is symmetric, we will have 6 unknowns. Okay, so there are total 9 unknowns in the equation. Okay, how many equations we have? So we have for a 3D flow, so this is for a 3D flow. Okay, so for total equations would be 3 momentum equation or 3 Cauchy equations plus 1 which is coming from mass conservation. Okay, so we have total 4 equations, right? So we have 9 unknowns but only 4 equations, so Cauchy equations are not solvable. Okay, so now we are going to eliminate this problem. Now we are to introduce some more formulations to make the number of equations equal to the number of unknowns. But now from now I'm going to assume that we are going to deal with incompressible Newtonian flow. Incompressible flow of a Newtonian fluid. Incompressible flow of Newtonian fluid. Okay, so until now whatever equations that we have considered, it is valid for solid and fluid, irrespective of whether the fluid is irrespective of whether the fluid is Newtonian, non-Newtonian, incompressible or compressible. Okay, but now the discussion that we are going to do from hereafter, it is valid only for incompressible Newtonian fluids only. Okay, and the resulting equations are called Navier-Stokes equations. Okay, now what we do as a first step is that we split the stress, we split the stress sigma into pressure plus viscous forces. Okay, so in matrix form we can write this as Z or sorry, let's deal only with fluid. Okay, so that would be equal to minus P okay, so what we have written here is just that we have split the stress we have into pressure component plus the viscous effect. Okay, so pressure acts equally in all direction. That is why the component of diagonal is P, and there is negative because it by pressure we are talking about compressive force per unit area. Okay, it is compressive, so it is negative. It will be equal in all directions, so the diagonal components have the same values. Okay, this is pressure force, this is viscous stresses. Okay, but this doesn't seem to be a clever idea, because now the total unknowns are 10. How? Because 3 velocity plus pressure plus 6 values of tau. Okay, this doesn't seem to be a clever idea, because instead of reducing the unknowns, we are actually increasing it. We have increased it by 1. Okay, but this decomposition expressed above helps us to write viscous stresses in terms of rate of strain tensor. Okay, so we can write viscous stress tau equals to 2 mu times epsilon dot. This is the rate of shear strain tensor, which we have derived while we were in the chapter kinematics of fluid flows. Okay, we have derived all the elements of this tensor. Okay, this is nothing. In the first class we have mentioned that tau is mu du by dy. Okay, we have introduced that this is the expression for Newtonian fluid, where the stress is directly proportional to rate of strain, and whatever we have written here is what we wrote here is the 3D generalization of this one-dimensional version what we have written here. So this is valid for 1D flow only. This is valid for all complex 3D flows. Okay, and here what we have written here, this expression is called constitutive equation for a fluid. Okay, by constitutive equation, this describes the behavior of fluid to the applied loading. This applied loading. Okay, so this is the constitutive equation for a fluid. So if this one we are going to substitute in the Cauchy equation to get the required equations. Instead of the constitutive equations for fluid, if you substitute the constitutive equation for solid, which is stress is proportional to strain, you will get governing equation for a solid. Okay, so the Cauchy equation is applicable for any type of medium, whether it is fluid or a solid. It is the constitutive equation that makes it more specific to the medium under consideration. Okay, and the constitutive equations are actually empirical relations. Okay, they are empirical relations. Okay, by empirical relation I mean this cannot be derived from first principles. By first principles we mean conservation of mass, momentum, or energy. You cannot derive this one from first principles. So this is an experimentally observed phenomena expressed in this form. Okay, you take fluid, you conduct a lot of experiment, you see that stress will be proportional to rate of strain. Okay, and this constitutive equation is valid for Newtonian incompressible fluids. Okay, so if you remember the elements of rate of strain tensor, the diagonal would be dou u by dou x, dou v by dou y, and dou w by dou z, which talks about normal strain, and off diagonal elements talk about shear strain, dou v by dou x, and it will be half dou u by dou z. Dou w by dou y. Okay, and this is symmetric. We have derived this in third chapter. Okay, but when we use the constitutive equation, it becomes so tau xx would be 2 mu dou u by dou x. Okay, and tau yx would be mu by dou x. Okay, you can write the other components also. but I'm going to talk only about the terms that are coming out in the momentum equation, the x direction momentum equation. Okay, so we have written this constitutive equation component wise. You can write the all six terms. Okay, now we come to the this decomposition. Sigma is minus p plus tau, so sigma xx is minus p plus 2 mu dou u by dou x. Sigma yx would be the same, okay, because only the diagonal component will get an additional pressure term. Zx. Okay, so if we go back to the momentum equation, or the x direction Cauchy equation, we have this term. Okay, now we are going to write this one. Okay, so we have 6x by dou x by dou y. Okay, so now if I write this, that would be minus dou p by dou x, okay, plus 2 mu dou square u by dou x square plus mu dou square u by dou y square plus mu dou square v by dou x square. Sorry, this will be dou x dou y. Okay, so now this will be the first term remain, dou p by dou x, plus let us combine these two terms to be mu dou square u by dou x square sorry, I have made a mistake here, sorry. So this would be, so we have to differentiate sigma yx with respect to y, so that would be dou square u by dou y square. This will be dou x dou y. Okay, so this will become dou square u by dou y square. Okay, plus we can write this, now we can combine the remaining part of mu dou square u by dou x square and this term as mu dou by dou x of d by dou y. Okay, so this is 0 due to continuity equations. Okay, for an incompressible flow, del dot u is 0, so this term goes to 0 due to mass conservation. Okay, so what we get is minus dou p by dou x plus mu plus dou y square. Okay, so similarly in y direction, what we would get is dou sigma xy okay. So when we substitute these two in Cauchy equation, okay, when we substitute in Cauchy equation, we will get okay, this is in x direction. Similarly in y direction, So these are the momentum equation for a 2D flow, and including continuity equation. Okay, we get, okay, these are together, they are called Navier-Stokes equations. Okay, this is one of the, or I would say one of the most important equations in fluid mechanics. Okay, and they govern the complete dynamics of incompressible Newtonian fluid. Okay, so now we have total unknowns. Let us write for 3D would be 3 velocity plus 1 which is pressure. There are 4 unknowns. Okay, so the total number of equations, we have 3 momentum plus 1 continuity. Okay, this is also equal to 4. So the number of equations are equal to number of unknowns, so they are possible to solve. Okay, but however, these equations are very complicated to solve mathematically. If you look at here, the nature of these equations are that they are partial differential equations. Okay, they are non-linear partial differential equations. Okay, which term is non-linear here? Okay, that the convective part, this is non-linear. Okay, it's an unknown u multiplied by the by another unknown, which is the gradient of the velocity. Okay, so this term is non-linear. They are coupled non-linear partial differential equations. By coupled, I mean there are, let's say in 2D there are 3 equations and 3 unknowns. We don't have a separate equation for separate unknowns. We have in total 3 equations in which all the unknowns appear. So these are coupled non-linear partial differential equations. So the exact solutions to these equations are not derived yet, except for very simple geometries with a number of simplifying assumptions. In fact, many researchers who have spent their lifetime trying to derive solutions for this, but still we are unsuccessful. Okay, so if you there is something called Clay Institute. Okay, they Clay Institute, it's an institute in US. They published number of unsolved problems in mathematics. Okay, and Navier-Stokes equation is, or whatever that we have written here, is one of the unsolved problem in mathematics. Okay, so you don't even have to derive the exact solution, but if one can prove that the solution exists and it is unique, okay, you are going to win $1 million as a prize. And also, I think most probably you will receive Fields Medal. Okay, do you know what is a Fields Medal? You can Google it. It's equivalent of Nobel Prize for mathematics. Okay, so we have derived one of the most important equations in fluid mechanics here. Take as much as time you need to understand the derivation, each and every step involved in the derivation. Okay, so we will stop by just doing like one more thing. So let us analyze this equation term by term. Okay, let us analyze this term by term. So I am writing x. I am dividing it by density, it doesn't matter, plus mu, this becomes kinematic viscosity. pi square. Okay, so this term talks about unsteady effect in the fluid flow. Okay, and all the unsteady effects are represented by this term, and this one talk about convective transport of momentum. Okay, so this is a non-linear term here. Okay, and this quantifies the pressure effects, and this is the viscous diffusion part. Okay, the viscosity diffuses momentum, and that is quantified by this term. Okay, it is these non-linear convective terms that adds a lot of difficulty to perform mathematical analysis, and also it is the same term that makes fluid mechanics very fascinating, and it allows to exhibit rich physical phenomena. Okay, so I'll stop here. This is very very important, so you should understand every step that we discussed here.